Hello, and welcome to Where Music Meets Science. My name is Scott Laird, and I'm a music instructor at the North Carolina School of Science and Math. Today, we will be introducing the term frequency and begin to relate the numerical information of frequency to the musical knowledge that you already have. Following today's lesson, you will have a working understanding of the term frequency, you will know the various parts of a sound wave, and you will be able to calculate octave relationships using your knowledge of frequency. So, without any further delay, let's begin.
Anytime you listen to music and sounds, I'm sure that you are aware that there are high-pitched sounds and low-pitched sounds, and many sounds in between. Great composers write music that has many pitches, ranging from high to low, and that keeps the music interesting. Many musicians choose their instrument based on the musical range of that instrument. That is, how high or low that instrument will play. One person may like the sound of a tuba, or string bass, while another may be drawn to the higher sounds of a flute or a viola. All of these various pitches are a result of sounds that are different frequencies. So, another way to think of pitch is to think of frequency. If an instrument has a high pitch, then it has a high frequency. If an instrument has a low pitch, then it has a low frequency. But the question remains, frequency of what? And how can it be measured? Well, here is where the science comes in.
Sound occurs when air molecules are forced together. After being forced together, they then expand farther apart, creating a wave-like motion of air.
Look at the cone of a stereo speaker as it is playing music with a loud beat. Notice how the speaker pushes out with each beat. This compresses air molecules and begins the wave-like motion. Here is another illustration of how it works. Air reacts in a manner that is very similar to water when a pebble is dropped into it, creating a series of waves that move out in a circular motion. Think of the water as the air and the pebble as the sound. The sound waves move out from the sound source in all directions, getting quieter as it gets further and further away. A small pebble can represent a high frequency or high pitch. It creates small waves that are very close together. A large rock can represent low frequencies or low pitches. It creates much larger waves that require much more space to develop. So, we can tell that the speed and the size of a wave relate to that wave's frequency. Also, we have learned that frequency is another term for pitch. But let's dig a little deeper. Let's look at the diagram of a sound wave. This is a diagram of the pitch A. It is the A above middle C on the piano. It is also the pitch that an orchestra traditionally uses to tune the instruments. Orchestras around the world tune their instruments to the pitch A. This is also often referred to as A440. 440 is the number that we're interested in today. Let's listen to the orchestra as it tunes. To unlock the secret of the number 440, let's go back to a diagram of a sound wave. This diagram represents the pitch created by a violin playing the tuning note A440. In order to unlock the secrets of the diagram, we must zoom in on the wave, just as if we were looking at it under a microscope. Now we are looking at a very small portion of that sound wave. We said earlier that sounds are created when molecules of air are forced together. The rise in the wave represents the time that the molecules are forced together. The fall of the wave represents the molecules pushing apart. So, the y-axis is air pressure. You will notice that it happens over and over. This takes time, so the x-axis represents time. One complete vibration of a wave is known as a cycle. And this is how we begin to relate these pitches to numbers. Can you guess how many complete vibrations or cycles an A440 goes through in 1 second? The answer is in the name of the pitch. If you guessed 440 cycles per second, you were absolutely correct. This single vibration actually occurs 440 times in 1 second. This is the wave's frequency, the number of cycles or waves that occur in 1 second. Let's look at how fast that really is. Anytime we hear that pitch, the A above middle C on the piano, it is the frequency 440 cycles per second. Let's listen to a few different instruments playing that same pitch or frequency. Another name for cycles per second is hertz. So we might say that you have just heard several instruments playing a pitch that is 440 hertz, or Hz. So, to more completely define frequency, it is cycles per second, or hertz. Now, let's take a look at some instruments that tune to pitches that are closely related to A440. First, let's listen to a cello tuning. Is the pitch that the cello is playing higher or lower than A440? If you answered lower, you were correct. In fact, it is 1 octave lower than the violin A. Let's take a look at the diagram of the pitch that the cello played. After seeing both pitches as diagrammed, can anyone guess the frequency of the cello? If you guessed 220, you are correct. When the cellist tunes their instrument, they hear an A440 and play an A220. This is because the cello is a lower pitched instrument. The cello's tuning note is A220 or 220 hertz. Here are some other instruments that tune to A220. Now let's listen to an instrument that tunes to yet another A. Is this A higher or lower than the cello A? If you said lower, you are correct. If the cello A is 220 hertz, then what is the tuba A? If you answered 110, you are correct. Let's look at a comparison of the graphs of each of these pitches. Let's listen to one more instrument playing yet another A. Using the formula that we have established, can you name the frequency of the bass's tuning note? The bass's tuning note is 55 hertz, or 55 cycles per second. Let's look at each of these numbers and try to find a pattern. Notice that as we move up 1 octave in pitch, the frequency doubles. Can you determine the frequency of the next octave above the violin? If you said 880, then you are correct. Might there be other frequencies that you could be interested in? Here are a few that you may find interesting.
This is the lowest open string on an upright or electric bass. This is the lowest open string on a guitar.
Let's review all that we have learned today. First, the sound is created by changes in air pressure. Second, these changes occur in a wave-like motion. Third, Faster waves or frequencies represent high pitches. Slower waves or frequencies represent low pitches. Fourth, one complete vibration of a wave is a cycle, and frequency or pitch is measured in cycles per second, or hertz. Finally, octave relationships between pitches are represented by a doubling relationship.
These mathematical relationships between pitches of frequencies can open a whole new world of understanding of music as you begin to use them more and more. In the next lesson, we will discuss the notion of complex waves and the unique sound of each instrument in the orchestra. I hope that you have enjoyed learning about frequency today and how it relates to our lives. I look forward to working with you again in the future. For now, so long from the North Carolina School of Science and Math.